Vamos.
Yo creo que sí. Carolyn, we begin the presentation. No, we begin with the introduction, the introductory words of the...
Buenos días a todos los que están presentes en el aula Miguel de Guzmán de la Facultad de Ciencias Matemáticas de la Universidad Complutense, y buenos días a todo el mundo que nos oye a través del streaming del canal YouTube de la facultad. Hoy tenemos el placer de realizar, y con bastante presencialidad, una nueva edición de la Conferencia Santaló. Y bueno, pues para nosotros el ir avanzando hacia la normalidad, y este es uno de los mejores puntos, pues desde luego es un aspecto importante. Hoy vamos a tener el placer de tener a una profesora de mucho prestigio, la profesora Carolyn Gordon del Dartmouth College, y que nos va a hablar de el título de una conferencia que va a ser Detecting or Not Geometry and Topology from Spectral Data. Indudablemente, la profesora Carolyn Gordon, como todo el mundo sabe, pues ha hecho unos trabajos realmente fascinantes, entre ellos uno que tituló en Scientific American, entre otros, si era posible escuchar la forma de una onda de tambor, ¿no? Hoy nos presenta también una conferencia sin duda muy atractiva y que seguro que lo vamos a pasar bastante bien. Quiero agradecer al profesor Marco Castrillón, director de la revista Matemática, la organización de todo este evento, al igual que el apoyo, como siempre, del personal de Administración y Servicios de la Facultad de Ciencias Matemáticas. En definitiva, quiero darles la bienvenida absolutamente a todos ustedes. Y bueno, voy a pasar simplemente a saludar a la profesora invitada de hoy, y posteriormente le daré la palabra al profesor Marco Castrillón, quien hará una introducción de las principales características científicas y de la carrera de nuestra invitada de hoy. Good morning, Caroline. I'm Antonio Bru, Dean of the Faculty of Mathematics of our university, and I am very pleased to present a lecture from you, and we'll be very delighted for all of us to meet you, and we would like to thank your willingness to give a lecture at our faculty. Santaló Conference is a very important event in our faculty because since it opens the academic year of our faculty. We have the pleasure for all people of having the author of such relevant research of the studying the possibility of hearing the shape of a wave from a drum. The topic that Professor Gordon is going to talk today is detecting or not geometry and topology from spectral data. With that, another fascinating topic. Professor Castrillón, director of the Revista Matemática Complutense, will make a presentation of Professor Gordon after me. I would like to thank Professor Castrillón for organizing this conference. Professor Gordon, once again, thank you very much for your lecture, and I am sure we are going to be very delighted. I give the floor to Professor Castrillón.
Muchas gracias, decano. Muchas gracias a todos y todas las asistentes y a las personas que están conectadas. Y bueno, mis agradecimientos más profundos a todas las personas que hacen posible estos encuentros científicos que, al fin y al cabo, forman parte del alma de nuestra institución. Y muchas gracias al decanato y a todo el personal que nos ha permitido contar hoy entre nosotros a tan distinguida conferenciante. So, Carolyn, I know you speak English and you speak Spanish, some words. So you probably have understood a little bit of what we have said. And we were expressing and conveying our deepest gratitude for accepting our invitation. So I'm going to switch into English. So again, thank you very much for attending this Santaló Conference 2021. And as you know, the difficulties due to the pandemic situation that we all know is imposing different conditions for this traditional scientific event. In the previous academic year, The lecture took place at the end of the second semester. And in this academic year, even though we recovered the position of this lecture as an opening event, we go through online, as many other conferences and workshops that we are following the researchers of this faculty. For this Santaló lecture, I'm deeply proud to introduce Professor Carolyn Gordon from Dartmouth College. Carolyn, first of all, thank you very much for being with us so early, because it's 7 a.m. in the States. So she woke up very early to share with us some geometry, topology, and analysis. That's fantastic. But waking up so early is very serious, so at least for me. So giving a lecture on spectral data at that time, for me, would be almost impossible. Not for you, Caroline, I'm sure. But okay, going back to serious words, I thank you very much for accepting the invitation. It's a great honor for us to have you as a lecturer, and we are very happy to share again a bit of our Complutense life, of the life of this university, since you were a visitor of our faculty some years ago. Welcome, at least online, again back home. Let me say some words about Professor Gordon. Our distinguished lecturer received her Bachelor of Science degree from Purdue University and earned a PhD degree from Washington University. Carolyn is a geometer. That's a fantastic word, geometer. A differential geometer, and has worked on many interesting topics. In particular, she's an expert, worldwide expert, on isospectral problems and homogeneous spaces. Isospectral geometry is one of those fantastic domains in mathematics where different fields meet and produce fascinating results. Analysis, geometry, topology, answering hard questions on the shape of a manifold from spectral data. That is, the eigenvalues of, I don't know, a differential operator. We may go back to 1992, when in collaboration with Professors Webb and Wolper, Professor Gordon gave a negative answer on the question conjecture of the determination of a shape of a drum or a Riemannian manifold or a Riemannian surface from its harmonics, from the eigenvalues of the Laplacian operator. And this was the beginning of a very long and fruitful story of extremely beautiful results on this isospectral geometry, the topic that we are going to enjoy in today's lecture. Carolyn has many other contributions. Actually, if I'm not wrong, the most cited of your papers, Carolyn, is on symplectic and Keller structures on nil manifolds, which is a fantastic paper, by the way. But I have to say that isospectral questions have been and are still the main trend in your work. Besides these solid mathematical contributions, Professor Gordon's career has been awarded with different distinctions and recognitions. For example, she earned the Chauvenet Prize of the Mathematical Association of America. She's fellow of the American Mathematical Society, and she's also fellow of the American Association for the Advance of Science. She was also the president of the Association for Women in Mathematics. I think that was in 2003 or 2004, I don't remember. In any case, I don't want to talk much more. Ladies and gentlemen, we have the pleasure of having among us an excellent lecturer who's gonna talk about an extremely beautiful topic. Thank you very much, Carolyn, and I give you now the floor for your presentation. The title was given by the dean before. I repeat, Detecting or Not Geometry and Topology from Spectral Data. Thank you very much, Carolyn.
Well, thank you so much for the really kind introduction and the wonderful invitation. It's a real honor to be back here. I had such a wonderful time at Universidad Complutense. A dozen years ago. The hospitality was just terrific. So I'm sorry I'm only there virtually, but it's really nice to be back. So thank you so much.
So I'm here to fix the screen things, and I think you are sharing. Okay, it's coming. We now here we are. So if you put it full screen mode. Here we are, and then.
Okay, I understand there's a bit of an echo. Are you able to hear okay, or?
Yeah, no, we don't hear that echo, so it's okay for us.
Okay, great. Thank you.
So I think, sorry, just a question. We have your presentation in full screen, and we have some small screens with you. I think it's better if we see Carolyn's face, right? Instead of having just the presentation, right? So I leave it as it is now, right? So the idea is that we have a big screen with your presentation, and then we have a small screen with you. Actually, if you still want to present some of these paper manifolds you talked about yesterday, I mean, perhaps you can do it because
okay.
we see you.
Okay.
But okay, go ahead.
Okay, so the problem I want to talk about is falls under imperspectral problems. And in imperspectral problems, the goal is to detect geometric or topological information about an object from spectral data. There's both direct and imperspectral problems. There's also a direct problem when it has the geometry and trying to find out information about spectrum. We'll focus mainly on the inverse problem. And the geometric objects we'll consider will be bounded domains in Rn, or more generally compact Riemannian manifolds with boundary. If you're not familiar with Riemannian manifolds, it's fine just primarily to think about bounded domains. Riemannian manifolds are just a generalization of Euclidean geometry where you have more general surfaces or higher dimensional manifolds. And a Riemannian metric gives you geometry, so a way of measuring distances and angles. And a given underlying manifold will have uncountably many Riemannian structures. And so you want to figure out exactly what geometry do you have. And the spectral data for us, what I consider two types of spectral data. There's the Laplace spectrum, which may be more familiar to many of you. And then the Stakloff spectrum, which is really taken off in the last couple of decades. And part of the goal of doing both of them is somewhat for comparison purposes. So the outline of the talk, I'll first introduce the spectra, and then we'll talk a little bit about asymptotics. Spectral asymptotics give you one method of extracting geometric and topological information. Then we'll go to the other direction and talk about constructions by spectral manifolds, which then give you information about geometric properties that are not determined by the spectrum. And then we'll talk about just a small number of sample open questions and progress. And again, what I'm going to talk about is going to be a tiny bit. I call it a survey. Okay, I am hearing a lot of echoes. You're not getting any problems? Okay. I just want to make sure you hear okay. So when we start with the Laplace spectrum, imagine you have a drum pad, which we view just as a bounded domain in the plane. Then the motion of the drum is determined by the wave equation, where the Laplacian is familiar Euclidean Laplacian. The minus sign here is just there to make the eigenvalues non-negative. And the stationary wave shapes are the solutions of the eigenvalue problem, Laplacian F equals lambda F. And because the boundary of the drum is held fixed, the function is zero on the boundary. So that's a Dirichlet boundary condition. And each time you have a function with an eigenvalue lambda, then you get characteristic frequency of vibration, square root of lambda over 2 pi, and F is the standing wave of that frequency. And so what I'll call the Dirichlet-Laplace spectrum of the domain is a collection of these eigenvalues counted with multiplicities. And so they completely determine the sound of the drum. And so Mark Katz's language, the inverse spectral problem, asks, can you hear the shape of a drum? From the eigenvalue spectrum, can you tell the geometry? For freely vibrating membrane, one instead looks at the Neumann eigenvalue problem. So Laplacian F is lambda F, now the normal derivative across the boundary is 0. One could also consider mixed problems like a broken drum. So now the stationary waves are eigenfunctions with boundary condition 0 on the part of the drum that's pinned down, and normal derivative 0 on the free part. And in all these conditions, you do have a discrete spectrum. And more generally, one can generalize everything to Riemannian manifolds. Our manifolds will be compact. We can consider manifolds with or without boundary. And I'm getting, my husband just mentioned that people listening online are getting a bad echo. There's comments on that in the chat. I don't know whether. Okay, thanks. So one can generalize to Riemannian manifolds. There's a natural notion of Laplacian, which is completely analogous to the Euclidean case. And one can, again, consider the eigenvalue problem. And if the boundary is non-empty, one can impose either Dirichlet or Neumann boundary conditions. And again, one gets a discrete spectrum. So that's the Laplace spectrum. Let me now introduce the Stakloff spectrum. And this actually goes all the way back to 1895, introduced by Stakloff. Again, Riemannian manifold with boundary. And if you prefer, again, just think of a bounded domain in Rn. And here the eigenvalue problem is somewhat different because the eigenvalue is in the boundary condition. So you're looking for harmonic functions, Laplacian equals 0, where the normal derivative across the boundary is a multiple of the function on the boundary. And that multiple sigma is your eigenvalue. And again, the sigmas for which a solution exists do form a discrete set, each occurring with finite multiplicity, going off to infinity. The spectrum can be viewed as the spectrum of a certain operator called the Dirichlet to Neumann operator, which I'll denote by D sub m. This is an operator not on the manifold itself, but just on the boundary. It maps smooth functions on the boundary to smooth functions on the boundary. So input a smooth function on the boundary. Then you know that it always extends uniquely to a harmonic function in the interior. So call that U tilde. Now, once you have that harmonic function, you can look at its normal derivative across the boundary, and that's your output. Hence, Dirichlet, you're inputting the Dirichlet condition for the harmonic function, you're outputting the Neumann. And these eigenfunctions of this operator provide an orthogonal basis of the boundary. And a condition, a sort of convention, even though technically the eigenfunctions live on the boundary, the harmonic extensions play an important role, so they're also called Stakloff eigenfunctions. In contrast to the Laplacian, which is a differential operator, the Dirichlet-Neumann operator, it's not locally defined. You have to extend the function to the whole interior to compute the value of the operator. And so it's just a pseudo-differential operator. Many interpretations. One is, if you want to go back to vibrating membranes, the Stakloff eigenvalues will be the characteristic frequencies of vibration of membranes in which all the mass is concentrated on the boundary rather than the interior. In terms of heat, well, harmonic functions are steady-state heat distributions. So these eigenfunctions are steady-state heat distributions for which the flux of heat across the boundary is proportional to the temperature on the boundary, the constant proportionality being the eigenvalue. A more interesting application, the Dirichlet-Neumann operator is also called the voltage to current operator, and it plays a key role in electrical impedance tomography, which is one of the reasons that interest is so much taken off on it. So the Carolyn's inverse tomography problem asks whether one can determine the conductivity of a medium from voltage and current measurements on the boundary. And that's the information that's basically contained in the Dirichlet-Neumann operator. And so there's applications in medicine. It's been used in dentistry, a lot of areas. A sort of fun interpretation for a mixed problem. So one could, instead of just considering the Stakloff problem, imagine here we have a cylinder, and on part of the boundary, the bottom and the sides, we're imposing, I'm calling N, the top is S, so two parts of the boundary. Consider the problem Laplacian equals 0, and the normal derivative is a multiple of f, so that's the Stakloff condition, but that condition only on the part of the boundary labeled S. On the rest of the boundary, just require the normal derivative be 0, like a Neumann condition. And this problem actually describes fluid motion, dynamics of fluid. You really imagine like a coffee cup, and the part of the boundary we call S, it's actually the open part of the container. And in 2012, Meyer and Khrushchevnikov won the Ig Nobel Prize for their paper, Walking with Coffee, Why Does It Spill?, which explains how the eigenfunctions of the Dirichlet-Neumann operator explain why your coffee spills. Sort of a very brief timetable. In 1895, Stakloff first introduced the Stakloff spectrum, but it lay pretty dormant for over a half century. And then Weinstock got a beautiful isoperimetric inequality showing the first eigenvalue, the first non-zero eigenvalue, multiplied by the length of the boundary is always less than or equal to 2 pi. So this is an example of a direct spectral result going from geometry to information about the eigenvalue for all simply connected plane domains. And as a consequence, we also showed equality if and only if the surface is, the domain is a disk, which as a consequence says that the disk is spectrally determined among all simply connected domains. And so that's inverse spectral result. In the next half century, there were scattered results, especially much more general inequalities on the eigenvalues. And then in the past 2 decades, there's been really dazzling acceleration. It's really taken off. I'm again going to focus on the inverse spectral problem, but I do want to mention the direct spectral problem of going from the geometry to the spectrum has had some really beautiful, beautiful work in it. But we won't go in that direction to keep this more contained. So let me first give you an example where you can actually compute the Stakloff spectrum. So let D of R naught be a Euclidean disk of radius R naught in the plane. Well, we're familiar with lots of harmonic functions on the disk, namely the spherical harmonics, which are if you think of R2 as a complex plane, these are just the real and imaginary parts of the holomorphic function Z the K. And so these harmonic functions are eigenfunctions for the Dirichlet-Neumann operator, because if you think what's the normal derivative across the boundary, it's just a radial derivative. And if you take the radial derivative, you just get K over R times the function. Boundary length is, the radius on the boundary is R naught, so the eigenvalue is K over R naught. And these restrictions to the boundary just give you the standard basis of L2 of the boundary, sines and cosines, so you know you've got everything. So the Stakloff spectrum is 0 for the constant functions, and then each K over R naught, each occurring twice. Okay, so let me now go to the spectral asymptotics and talk about geometric topological information contained in the spectrum. So notation, I'll say two sequences of real numbers are asymptotic if the corresponding entries differ by order j to the minus infinity. So they're becoming extremely close. And I'll use this notation STEM for asymptotic. Actually, before I go there, if you think about how the Dirichlet-Neumann operator is defined, starting on the boundary, extending the functions harmonically, and then going back to the boundary, and if you think about the various interpretations of it, you might expect that the information contained in the spectrum, it should have more information about the region close to the boundary than the region further in the interior. And this is captured very nicely by a theorem of Hislop and Lutzer, valid in all dimensions, that says, suppose you have two Riemannian manifolds with smooth boundary, and suppose that some neighborhoods of their boundaries are isometric to each other. In other words, here we have two drawn surfaces, so this is valid in all dimensions. We have two boundary components in each one, and these little yellow collars about the boundaries are identical. Then you're guaranteed that their Stakloff asymptotics are the same. Of course, not the same spectrum, but the same asymptotics. And for those of you familiar with pseudo-differential operators, this really comes from the fact that the symbol determines the asymptotics, and one shows that the symbol is supported in a neighborhood. Just really depends on geometry in a neighborhood. Now, in two dimensions, one can say much more. Very special to dimension 2 is that conformal changes in the metric in the interior of the manifold, as long as you don't change the boundary, do not affect either the Dirichlet-Neumann operator or its spectrum. And the reason for this is that when you change the metric just by multiplying by a conformal function, in dimension 2, the Laplacian just gets multiplied by 1 over that function. And so its kernel, the harmonic functions, don't change. In higher dimensions, you also get a lower term, and so this doesn't carry over. So in particular, a flat disk and a hemisphere, for example, of the same radius. So this hemisphere here, the surface is just the round surface. The bottom disk is not included. So they have the same boundary, this little red circle here. They have the same Stakloff spectrum because the hemisphere is conformally equivalent to the disk by stereographic projection. Now, using the theorem of Hislop and Lutzer that says that the spectral information just contained in the asymptotic information just depends on a color neighborhood, and then using this further information about conformal metrics, Girard, Parnofsky, Polterovich, and Schur show that in the case of surfaces, so two-dimensional with smooth boundary, all you need is isometric boundaries in order for two surfaces to have the same asymptotics. The idea is you take your little color neighborhoods of the boundary, separate them out, fill them in topologically with disks, and then use uniformization to kind of flatten things out. And so, in particular, any surface whatsoever has the same Stakloff asymptotics as a union of disks, where you just make the disk have the same boundary as the various components of your surface. You know the asymptotics of disks. We already looked at those. We know the spectrum. And so you actually know the asymptotics precisely. And from this, they were able to show that for smooth surfaces, the Stakloff spectrum determines both the number of boundary circles and their lengths. Now, the corresponding question in higher dimensions is completely open. From the Stakloff spectrum, can you determine the number of boundary components? It's known that you can determine the whole entire volume of the boundary together, but nothing about individual components or their number. Okay, so that was Stakloff asymptotics, but there's also another way of getting asymptotics through heat invariance that's applicable to both the Laplace and the Stakloff setting. And so I'm going to back off Stakloff for a little while, go back to the Laplace setting to introduce the heat asymptotics, and then we'll come back briefly to the Stakloff setting. So the whole so-called heat expansion, first we're going to imagine a compact manifold, Riemannian manifold without boundary, so a closed manifold. And its Laplace spectrum is a collection lambda sub j. Then we talked about the wave equation before. Similarly, one can look at the heat equation. It has the fundamental solution, and if you take its trace, there's this asymptotic expansion of the following form. The left-hand side is completely just is encoding the spectrum and is determined by the spectrum, lambda j, so the eigenvalues. And so everything on the right-hand side is spectrally determined. In here is the dimension, and these A's here are universal expressions that just involve integrals of curvature expressions on the manifold. And so everything is a spectral invariant. So the spectrum determines n, which is the dimension, A0, which is the volume, A1, which is the total scalar curvature, and in dimension 2, scalar curvature is just Gauss curvature. Gauss-Bonnet theorem says when you integrate that, you get the Euler characteristic. And so in dimension 2, the spectrum of the Laplacian tells you the topology completely. That's not true in higher dimensions. There's counterexamples. They get more complicated. A2, don't worry about what these expressions are, but it's a very specific linear combination of 3 curvature expressions. I always used to think that these complicated expressions were just kind of a weakness in the heat invariance as opposed to weakness in the spectrum, but that apparently is not the case. The heat invariance may be as good as it gets for this type of invariant. Dorothée showed that these 3 individual integrals in A2 are actually not spectral invariants. She used the Taurus action method that we'll talk about a little bit later to construct pairs of manifolds that have the same Laplace spectrum, but for which these 3 expressions are different. For manifolds with smooth boundary, one again has an asymptotic expansion, but now you have half powers occurring as well, and the half power terms come from boundary information. So for example, A1 half is a constant. These constants depend only on dimension, times the volume of the part of the boundary where you've imposed Dirichlet boundary conditions minus the part of the boundary where you've imposed Neumann boundary conditions. So in particular, in the case one usually considers where you're either looking at the purely Dirichlet boundary conditions or purely Neumann boundary conditions, then the spectrum is telling you the volume of the boundary. So in the language of Mark Katz, the boundary volume is audible. You can tell it from the spectrum. But again, the fact that the mixed condition, this can cancel, is not a weakness in the spectral invariance. Levitin, Parnofsky, and Polterovich constructed pairs of domains with mixed boundary conditions whose total boundary volume is different. The total boundary volume is not audible. Here they are. On the first domain is the square. Everything else, the triangles and the F and G are just there for the proof that I'm going to explain. But each of these domains, the square and this triangle here, are made up of 2 right triangles. All 4 right triangles are congruent to each other, and they're color-coded so you can see how they're glued together. Where you see solid boundary edges, that's like the part of the drum that's pinned down. So that's Dirichlet boundary conditions on that part. Where you see a dashed edge, that's the broken part of the drum. That's where we're imposing Neumann boundary conditions. And so why do they have the same spectrum? Well, imagine you have an eigenfunction on the first domain, say eigenvalue lambda. Restrict it to the 2 triangles making up the domain, then they're both eigenfunctions with eigenvalue lambda on the triangle, but with the appropriate conditions. F here is 0 on the blue and black edges. G is 0 here, normal derivative 0 here, and F and G fit together smoothly on the red edge. Now, since they're both lambda eigenfunctions on the triangle, we can take these linear combinations to get eigenfunctions on the triangle. Why do we have the correct boundary condition? Well, there's 2 things we have to check to see that we're actually getting the eigenfunction here. One is that they fit together smoothly, which I'll come back to in a second. And the second is that they have the correct boundary conditions. Well, let's check the boundary conditions first. On the black edge, everything was 0, so these combinations are 0, no problem. On the red edge, F and G share a red edge, and so they agree there. So minus F plus G gives you 0 there. On this edge, we want normal derivative 0. Well, notice that the outward normal coming from F is the inward normal into the triangle with the function G. And so the outward normal derivative of F coincides with the inward normal derivative of G. And so going backwards, the sum of their outward normal derivatives, they're opposite, they cancel out to 0. So you have Neumann boundary conditions here. Now, why they fit together smoothly, well, let me go to the reflection principle. So here we have a triangle. If you have a triangle, you have an eigenfunction which has 0 boundary conditions on, say, this red edge here. These eigenfunctions are actually analytic, and there's a reflection principle that says if you reflect it to its negative across that boundary edge, it'll be smooth. Here's a picture. And similarly, if you have normal derivative 0 across that edge and you reflect it evenly, it'll be smooth. And that's exactly what's happening here. F on the blue edge is 0, so it reflects smoothly to its negative. G on the blue edge has normal derivative 0, so it reflects smoothly to G. And so what we've done now is we've constructed an eigenfunction on the second domain with the same eigenvalue. And this is very easily seen to be invertible process. And so we've gotten all the eigenvalues this way, so they have the same spectrum. So this is the idea of transplantation that we'll talk about a little bit later. So let me now go back to the Stakloff setting after that distraction. There's also a heat expansion for the Stakloff spectrum, much more recent. This is by Polterovich and Schur in 2015. Again, an asymptotic expansion as t goes to 0. The sigma j's are all the Stakloff eigenvalues. On the right-hand side, it's a similar type of expression. N is the dimension of the manifold, so n minus 1 is the dimension of the boundary, which is what you expect to be relevant when you're talking about the Stakloff spectrum. And then these AJs and BKs are universal expressions, universal constants. And depending only on the geometry. And the log t here, we have the log terms here, which was different from the Laplace case. But again, the AJs, the BKs, the N are all spectral invariants. So the spectrum, I'm sorry, this should say STEC instead of spec. This is the Stakloff spectrum. The Stakloff spectrum determines the dimension, A0, which is the constant times the volume of the boundary. A1 is the total mean curvature of the boundary. They also computed A2, but it's more complicated. There's a huge literature for the Laplace spectrum on applications of heat invariance. So let me just mention a couple examples. So for the Laplace spectrum, in dimension less than or equal 6, using heat invariance, Tano showed that the standard round metric on the sphere is spectrally determined among all possible geometries on the sphere. That's only known up to dimension 6. In higher dimensions, we still don't know whether the Laplace spectrum tells you whether a metric on an underlying sphere is round or not. You could have mountains and valleys. And is that spectrally determined? Now, on the other hand, a very elementary result in Rn is that balls are spectrally determined after translation among all domains in Rn. And this is very easy to see because this is assuming you have either Dirichlet or Neumann boundary conditions, not mixed. Because you know the spectrum determines the volume of the manifold and the volume of the boundary. And so the isoperimetric inequality tells you whether you have a round ball or not, a standard ball or not. Now for the Stakloff spectrum, the Polterovich and Schur, using their heat invariance, were able to show that balls are spectrally determined among simply connected domains in R3, so three-dimensional balls are determined. Weinstock already showed two-dimensional case, as we talked about before. Higher dimensions, it's still wide open for the Stakloff spectrum. But lest you think the Laplace spectrum is so far advanced in comparison, still open even for the Laplace spectrum is, can you even tell whether a Riemannian manifold is flat or not? We still don't know that. Okay, so now let me shift gears and talk about ways of constructing isospectral manifolds. And the methods we're going to look at were developed in the Laplace setting, but mostly go through in the Stakloff setting as well. And I want to look at two techniques. These are sort of two general techniques that have been used. There's also various isolated examples by direct computation and other methods. The first of these methods is definitely the most widely known and widely used. It's very fun and elegant. A technique due to Sonata, which gives you manifolds that have the same local geometry. So, for example, plane domains locally all look the same. They're just flat. You need to see the global structure to know they're different. And then the torus action technique, which actually gives you manifolds with different local geometry as well. So the curvature properties can be different. And then we'll look at, well, yeah, that's where we're going. So let me start with Sonata. So to introduce it, we need to start with finite group G and a pair of subgroups, gamma 1 and gamma 2. And we say they're almost conjugate in G if each conjugate class in G intersects gamma 1 and gamma 2 in the same number of elements. Another way of saying the same thing is that there's a set bijection between gamma 1 and gamma 2, which is only a bijection of sets, not a homomorphism necessarily, that takes such that each element in gamma 1 is conjugate in G to the corresponding element of gamma 2. Of course, one way of getting almost conjugate groups is by taking conjugate subgroups, but that's not interesting. And the construction we'll be giving, if you do that, it will just turn out to get isometric objects and it won't be of interest. Now, this almost conjugate condition can be rephrased as a representation theoretic condition. So again, suppose you have a finite group G and a subgroup gamma, then you can take the coset space, which is just a finite set, G mod gamma, and you can form a vector space by taking all formal linear combinations of elements of G mod gamma. And the group G will act on this vector space because G permutes the cosets by left translation, and to extend that to a linear action on this vector space, permuting these basis elements. That's a linear permutation representation. And Gospin, back in 1926, showed that two subgroups of a finite group are almost conjugate if and only if these representations are equivalent. That is, there's a vector space isomorphism that intertwines the G actions. Okay, so you can think either way, almost conjugacy or representation equivalent. And Sonata's technique is very simple. It says, suppose you have a compact Riemannian manifold with or without boundary, and let G be a finite group of isometries of M. And suppose that gamma 1 and gamma 2 are almost conjugate subgroups. So here's M. You can quotient out by gamma 1 and gamma 2 just by identifying elements that differ by one of these isometries. And if the groups are acting freely, then what you get downstairs will be manifolds. If not, you get orbifolds. But think about the free case. And the metric on M gives you a metric downstairs. And Sonata show that the simple condition implies that these two quotients have the same spectrum. And then more recently, Peter Herbert, David Webb, and I showed they also have the same Stakloff spectrum. And it's really the same argument, same construction and argument. In fact, basically any type of spectral problem you're going to put on these, any reasonable spectral problem will have the same spectrum. So here's an example. Let G be the group of 3x3 matrices over the two-element field Z2, so entries 0s and 1s. And let gamma 1 be the matrices whose first column is 1, 0, 0. Everything else is arbitrary as long as you have determinant 1. And gamma 2 is the transpose of gamma 1. And it's easy to see that each element in gamma 1 is conjugate to its transpose in gamma 2. So these are almost conjugate, but they're not conjugate subgroups. And the index is 7. And for purposes of drawing the Schreier graph for the moment, I want to mention that G can be generated by two elements, two specific elements. Now, what you see here is it's called the Schreier graphs for these coset spaces, G mod gamma 1 and G mod gamma 2. They're analogous to Cayley graphs for groups, but they're for cosets. Remember, the index of gamma 1 and gamma 2 and G was 7. So there's 7 cosets. We've labeled the cosets 0 through 6. So there's one vertex for each coset. And we had a generating set of two elements, A and B. So there's a red edge joining vertex 0 to vertex 1. That indicates that if you take the coset labeled 0, multiply it by the group element A, you get the coset 1. So these Schreier graphs totally encode the action of G on the cosets. And you could also take the Cayley graph, which is formed the same way using all the group elements as vertices. It'll have 168 vertices. And then they're joined according to how the generators act on the group elements. And if you're interested in spectral theory of graphs, Sonata's theorem also works in that setting. The Cayley graph covers these two graphs. You take the Cayley graph, quotient out by the action of gamma 1 and gamma 2, and you get these Schreier graphs. And Sonata's theorem will guarantee that these are isospectral as graphs. Now, Peter Buser first introduced the idea of using Sonata's method to construct isospectral manifolds just by gluing together tiles in the shape according to the pattern in the Cayley graphs. So here he's glued 7 crosses together using the exact same pattern. And these 2 surfaces, they're just flat surfaces sitting in R3. In fact, I guess you can see. So here they are. Hold them up in the same way. Oops. So here they are. You can make them out of paper. And these will have the same spectrum. Sonata's theorem, you need, remember, Sonata's theorem says you have a manifold M, and you take quotients by these groups gamma 1 and gamma 2. They're almost conjugate in some other group. The manifold M that covers these is just formed from the Cayley graph of G with 168 crosses glued together according to that pattern. So these will be isospectral. You can put either Dirichlet or Neumann boundary conditions on the boundary as long as you're consistent, and they'll be isospectral. And one geometric property you can see that's different is diameter, the distance from the tip of this claw to the tip of this claw down here, this point to this point, is greater than the distance between any 2 points than the other. So let me come back to this notion of transplantation and that we looked at before, and where does it come from? And this concept was introduced independently by Pierre Berard and Peter Buser. And Steve Zeldich also had a version of it. And then it's been developed further over the years, and many sort of generalizations. It's kind of taken off by many people. So going back to our original group G, which is SL3 over a 2-element field, and we have these 2 subgroups, gamma 1 and gamma 2. And remember, this almost constancy condition was equivalent to saying that the linear permutation representations are the same. Again, these coset spaces are 7-dimensional. And you can write down the intertwining operator that intertwines the group actions very explicitly in terms of, remember, we labeled our cosets, we ordered them 0 to 6. So this is a matrix of an intertwining operator in terms of the bases for the cosets that we took, the bases of these 2 vector spaces consisting of the cosets. So the idea of transplantation is start with a function on, it goes backwards. So start with a function on the second domain, and this is actually the second one here. I've drawn them in reverse order. And take a function on that domain, say an eigenfunction for the Laplacian, and let F0 to F6 be its restrictions to the 7 crosses making up this domain. And since the crosses are labeled according to the cosets, we know exactly how we're assembling it. Now, we obtain a function on this other domain by taking the matrix that we saw that intertwined the linear permutation representations, multiplying it by this column of functions. We get a new column of functions, which we can view as functions on the 7 crosses making up the second domain. So we just assemble them. H0 goes on this cross labeled 0. H1 goes, I guess it down here on the cross labeled 1, and so on. And you're guaranteed that they fit together smoothly. The guarantee comes from the fact that the linear permutation representations, which gave you the gluing patterns for these Schreier graphs, that they're equivalent. And the Stakloff spectrum, everything works the same way. These are Stakloff isospectral as well. because the Stakloff conditions are linear conditions and everything goes through exactly as before. The same transplantation works. So these are Laplace isospectral and Stakloff isospectral. Now, if you look at these two domains, you'll see that they have a symmetry front to back, a reflection symmetry, symmetry the plane of the screen if you're looking at the PDF. And if you quotient out by that reflection, then what you get looks like a plane domain. And so the second one, for example, is what you get by flattening out this surface here. And here's the other one flattened out. And this reflection is another symmetry which kind of fits together with the group of symmetries in Sonata's theorem to give you a larger group to which you can again apply Sonata's theorem to get that these domains are Laplace isospectral. And I'll come back to the issue of Stakloff in a few minutes. There's a little caution here that we'll come back to. So these were the first examples of isospectral plane domains by David Webb and Scott Walpert and myself. And the transplantation method gives you, here's the proof. This is the one for the Dirichlet transplantation. For the Neumann transplantation, just make all the minus signs pluses. And I have to admit, I'm lying to you a little bit and saying that Dirichlet comes for free from Sonata. What comes for free from Sonata is actually the Neumann isospectrality. The reason for that is that, which I'll come back to, is when you mod it out by this reflection, part of the boundary that you get when you go to the quotient really came not from the boundary of the domain, but from the fixed points of the reflection. And so there's a little bit of extra work you have to do to get to the Dirichlet. But once you have the gluing pattern and you have this transplantation, you can simplify the shape. And so replacing these sort of half crosses by triangles, Berard and separately Peter Buser and Klaus-Dieter Simler got these much simpler examples of isospectral plane domains with the same transplantation proof. So are these plane domains Stakloff isospectral? Peter Buser's surfaces were, these original surfaces are isospectral. The plane domains, probably not. However, they are splotching isospectral. That is, they're isospectral for a mixed Stakloff-Neumann problem. And again, the issue is that these red edges here on the boundary were not part of the boundary of Peter Buser's manifolds, but rather the part of the boundary that was fixed by the reflection. And the eigenfunctions on the quotient by the reflection pull back to eigenfunctions for whatever problem we're talking about here, Stakloff, on Peter Buser's surfaces, but they're going to be reflection invariant. And if you look at a function that's invariant under the reflection, then when you take this normal derivative across the boundary, when you go to the quotient, you're going to get 0. And so that's why you only get we had to impose Neumann conditions on these red edges. Okay, so that's the Sonata's technique. I wanted to go into some detail because I want to kind of make a plug for it in whatever area of mathematics you work in. If you're looking for counterexamples, you might want to think about Sonata's theorem. The original motivation for Sonata actually came from a theorem of Gossman back in 1926, where he used these almost conjugate subgroups to construct non-isomorphic number fields with the same zeta function. So counterexamples to the question, does the zeta function determine the number field? An example in algebraic geometry, Dipendra Prasad and Rajan constructed Riemann surfaces with isogenous Jacobians using sort of Sonata technique. And Iran Makover, David Webb, and I gave sort of a transplantation proof of this, which is kind of fun. And then more recently, Arpora, Katz, Reynolds, and Sola Porcar gave many examples, many applications in algebraic geometry. One of them is written here, projective varieties, all of whose intermediate Jacobians are isomorphic, and many other things as well. Again, we gave sort of a transplantation argument afterwards as well. And so what else? You know, if you're looking for counterexamples in your area, you might want to look here. Let's see, I'm getting short on time, so I'm just going to mention the torus action technique very briefly. And so the torus action technique, the idea is that you show a pair of manifolds have the same spectrum by sort of doing the opposite of what we did with Sonata. We show that they have lots of quotients that are isometric or at least isospectral, and set up in such a way that the spectrum of the quotient is part of the spectrum of the manifold, that the eigenfunctions downstairs lift to eigenfunctions here. So each quotient that's isospectral tells you part of the spectrum of M1 and M2 are the same. And if there's enough of those and you can sort them out, then you get the M1 and M2 are isospectral. So it's kind of the opposite of what we did from Sonata, where we looked at quotients. We showed quotients for isospectral. Here we're going up to the top. The torus action method, I introduced the earliest version in 1994. There's been many versions since. The state-of-the-art is Dorothee Schutz's version. And recently, Peter Herbert, David Webb, and I showed again that everything goes through for the Stakloff spectrum. And it involves torus actions. I think I'm going to skip over that and just give you one application. So this can give you isospectral simply connected objects, and combining the results from for the Laplace spectrum, going back to Dorothee Schutz in the lowest dimensions and myself in the higher dimensions, and recent work of Peter Herbert and David Webb and myself for the Stakloff spectrum, we have the following. In every dimension 6 and higher, one can get actually continuous families of different non-isometric volumetrics, so different geometries on the n-dimensional ball Bn, such that all the metrics are Laplace isospectral, where you can impose either Dirichlet or Neumann boundary conditions, and they'll be isospectral. The induced metrics on the boundary sphere are isospectral for the Laplacian, and all the metrics on the ball are also Stakloff isospectral. Okay, so let me go to a few sample open questions in progress to end. For plane domains, it's still wide open whether you can hear the shape of convex plane domains. All the counterexamples are non-convex. All of them have corners without smooth plane domains. Some progress, very deep work of Steve Zeldich among analytic convex domains with a certain amount of symmetry. Each domain is uniquely determined within that family by its spectrum. And he strengthened this in 2010. Can you hear whether a domain has corners? Say domain in the plane. And this is quite recent work, Roulette and Lou for the Dirichlet case, yes, for simply connected plane domains. Nur-Sultanov, Roulette, and Schur, even later, did the Neumann case that simply connected polygonal plane domains. They have to be polygonal here. These others can be just any curvilinear, are distinguishable from smooth domains. And then very recently, preprint, a very, very major work, yes, for simply connected curvilinear domains and arbitrary surfaces. But can you hear this number of corners wide open? Can you hear the angles at the corners? Well, yes, for triangles, and very recently, non-obtuse trapezoids, but otherwise wide open. And how about for the Stakloff spectrum? Well, let's ask the same question. Does the Stakloff spectrum detect corners? Remarkably, I mean, thinking about the fact that the Laplace result was just attained, Krimsky, Levitine, Pardnovsky, Polterovich, and Schur, using totally different methods special to the Stakloff spectrum, in two very long, deep papers, prove that for generic curvilinear polygons in the plane with all angles less than pi, the Stakloff spectrum detects not only the number of corners, but also the lengths of the curvilinear segments in order, and the angles at the corners up to an equivalence, which just has to do with taking complementary angles. So quite remarkable result. Tim, a couple other questions. We don't know whether there's isospectral plane domains or Stakloff isospectral. Also, the only methods that have been used to construct isospectral manifolds are ones that were first developed in the Laplace setting. So we don't know whether there's Stakloff isospectral manifolds whose boundaries aren't already Laplace isospectral. So I'll end there. Thank you very much. Oops. Oh, this might be confusing. I should stop. No. Oh, thank you. Appreciate it.
microphone to one of the professors here. Sí. Okay, perhaps Josechu, if you can hear, or I'm sorry for the technical difficulties of these online lectures.
Ponte por el otro lado y te ve.
Hi. I have one question, and is what are the less restrictive conditions that you can require on a plane domain so you can hear the shape? For instance, convex plane domains with polygonal with a finite number of sides.
Oh, okay. Can you tell the shape of a polygonal domain with a finite number of sides? That's still open. It's only known for triangles and obtuse trapezoids. Otherwise, we actually don't know. Yeah. Mm-hmm.
Does anyone else have a question? So here we are.
Okay. Hi. So thanks for the talk. In the first construction you showed to make isospectral manifolds. Can you go back to the presentation? Well, okay. Can we just instead of having only one manifold M and taking the two quotients, can we have two spectrally symmetrical manifolds M and M prime and take quotients in the different manifolds and deduce that these manifolds are also spectrally isospectral related? I don't know.
I'm sorry, I wasn't able to understand the question. Oh, I see. Let's see. Trying to remember now what, because there is a result of Craig Sutton. Why am I? For some reason, because early in the morning, I'm drawing a blank on what the I believe that for some reason I'm drawing a blank, and I'm actually not sure of the answer. There is sorry, I can actually check and look that up. For some reason, I'm just drawing a blank.
So it probably goes to the list of open problems. So that's
Well,
another open problem. So I have another question in case it's another new question in terms of another member of the list of open questions. What about pseudo-Riemannian manifolds and Lorentzian manifolds where the Laplacian is not elliptic, but now it's going to be a hyperbolic operator? So techniques doesn't work, and things are completely different. But do we have answers and questions about isospectrality in Lorentzian manifolds?
That's an area that I really don't know. One can do hypoelliptic. You can do like CR manifolds and things, but I don't know about pseudo.
Still more questions, open questions. That's good. Is there any other question from here or online? That's great. I think that was the last question. So we're about to close the lecture. And the tradition is inviting the speaker to a good lunch in a good restaurant. And actually the dean pays for that, but unfortunately we cannot do it. In your case, that should be a breakfast, not a lunch, but I think that invitation is for the future, for the next time you are visiting us. So please come to Madrid again, and at least you will have a good lunch. And I hope you will have some interesting mathematical conversations as well.
Well, thank you, Ray.
You're welcome. So thank you very much, Professor Gordon, for your lecture. And with this, we finish our Santaló lecture. Thank you very much to everyone. And as I said before, the lecture will be posted in the YouTube channel of the faculty for future convenience. Thank you very much, Professor Gordon.
Thank you.